Okay, and it is working as I thought. So let me hand over the floor to group 8.
All right, here we go. Hello, everybody. Thank you so much for coming out. We are group 8, the dual wing heliostat. My name is Joseph Rios.
I'm Nathan Brett.
I'm Kat Hutt.
I'm Carl Justino Ortiz.
I'm Trevor Perez.
I'm Sam Scholl.
Devin Yan.
The reflector subsystem features 4 silver-backed mirrors mounted at an angle to produce an artificial concavity that will help in focusing the light on the central tower. The reflector mount is made of injection molded ABS plastic that utilizes snap fits to easily install or replace the mirrors if necessary. Each mount is attached to the actuation subsystem using 2 bolts to further simplify the design.
The actuation subsystem tracks the sun 350 degrees along the azimuthal axis and 360 degrees along the altitude axis. The altitude axis is driven by a servo stepper hybrid motor, and the azimuth axis is driven by a DC gear motor.
The control subsystem is made up of a microprocessor controller, as well as 2 motor drivers that are going to power and support the DC motor, as well as the stepper hybrid motor interfacing with the actuation subsystem.
All right, so our base subsystem is made out of off-the-shelf square CPVC. The base has 2 end connections that are based on off-the-shelf parts that we found and connect the square tubing to the root system you see at the bottom. The root system is buried in the ground to add support to the heliostat structure and also to reduce costs. The base also has a door that houses the controls, as you can see on the top.
Our hedgehog concept focuses on the convergence of simplicity, cost, and efficiency. When you maintain simplicity, many other items will slowly fall into place behind it. For instance, it will keep costs low, materials become easier to purchase off the shelf, and assembly and manufacturing time are reduced. Further, the end goal for this heliostat module is ultimately to use these small modules in a field of hundreds, perhaps even thousands. So the less complex a smaller module is, the easier it will be to implement. Each module is controlled with its own microprocessor board, which takes in local data per heliostat and reports this information back to the central tower, allowing the central tower controller to optimize the entire solar field for maximum efficiency. The module's reflectors are mounted in a window pane arrangement with their corners tilted in towards a central vertex, optimizing the focus of heat and light delivery. All of our motivations were inspired by the customer needs statement and will be further reinforced in the coming slides.
Circling back to our final design, let's dig into how these motivations and goals informed our design process for the reflector subsystem. Going through the next few slides, here's a nice little preview of the method for inserting the reflectors into their mount, which uses snap fits. And now we'll get into the focusing power of this module. With a total reflective surface area of about 1.07 meters squared and a reflectivity of 0.09 or 0.97, thanks to the silver-backed mirrors, we calculate that on a sunny day under ideal conditions, it would require only 960 modules to deliver 1 megawatt of power to a 1 meter squared receiver. Rounding this up, we made all of our bulk pricing estimates, assuming that the field would be composed of 1,000 heliostat modules. Helping to theoretically lower the number of modules needed to reach that 1 megawatt of power is the slight angle that we added to the reflectors, which we should theoretically help with focusing the light as well as combating dispersion.
Following the overarching theme of our project motivations, the steps for mounting the reflector subsystem to the crossbar were kept as simple as possible. Once the 4 reflectors have been placed into the reflector mounts and locked in place with the snap fits, the frame is ready to be attached to the crossbar. To further ease assembly, the crossbar has pre-drilled holes for the mount's hardware. 1 reflector mount with 2 mirrors is slid onto the crossbar using the molded supports. 2 1/4" by 20 bolts are inserted into the relevant holes, 1 for each molded support. A 1/4" by 20 nut is attached to each bolt and an end cap is placed on the crossbar, finishing the assembly of the reflector mount to the actuation system. This process is repeated for the second reflector mount on the opposite side of the crossbar. To simplify the ease of assembly and number of parts, the reflector mount is designed to be molded as one piece. The mount was also molded as one part to increase its rigidity since the material was removed from the reflector's backing. The back surface of the mount has cutouts in it to reduce the weight and cost of the material needed for manufacturing. The method of manufacturing chosen for the reflector mount is injection molding. This process is ideal for its ability to quickly create a large quantity of parts that meet the design requirements. Injection molding is useful for this application because the reflector mount is a unique design, and a new mold will need to be created. An Ashby plot for stress and maximum surface temperature was used to assist in choosing the material for molding. ABS plastic was chosen to be the material for the mount as it is routinely used in injection molding, resulting in lower costs from its availability. The plastic expanding and putting too much force on the reflectors, causing them to fracture, was a concern. However, the Ashby plot proved that even with a record high temperature of 47 degrees Celsius in Las Vegas, the plastic would hold up.
So with this reflector subsystem, we were able to link 8 customer needs together and use them to come up with quantitative metrics that informed the design decisions for this subsystem, which included how many heliostats to include per module, what material properties would be needed, how important the assembly time and number of parts were, and the overall geometry of our reflective surface. Using the metrics allowed us to select what concept for the reflector we should move forward with. And we kept them in mind as we were making design changes throughout the entire process of integrating the reflector to the rest of the subsystems and also integrating feedback about our design. Getting into the details of the reflector design, we start with the angle of the reflective surfaces. While dispersion is a rather complicated calculation that we were advised not to try to dive into, we still wanted to design something to minimize how much light was missing the receiver. Since we have flat mirrors, we figured that if we angle them slightly inwards, we can make sure the light from the edges of the mirror is still pointing into the receiver instead of missing it possibly. Deciding on this angle of tilt inwards is a simple matter of geometry. For a mirror with a set width and distance from the receiver, we can make a triangle and create an expression for the theta ref, the angle of the reflector, based on d rec, the distance to the receiver. Using this method, we decided to optimize the design for a heliostat at 50 meters from the receiver tower, which comes out to an angle of 1 degree. If the field were to be designed differently, it would be easy to change this design and either increase or decrease that angle. But with the 1 degrees, we recommend that heliostats be placed no closer than 40 meters and no further than 60 meters from the receiver. You can see the optimal angles for those particular locations as well on this slide. Next up is the method of securing the reflectors to their mount. We used snap fits as part of our solution to reduce part count and assembly time. The design of the snap fit is based around ensuring that the bending stress at the base of the snap fit does not exceed the yield stress of the ABS plastic the mount is made out of. The force the snap fit experiences is purely due to the displacement at the top, which is determined by how much the dwell face is offset from the post. This measurement is marked as E in the diagram on this slide. By setting the deflection of the snap fit, which we modeled as a beam, equal to E, we were able to find an expression for the force that the snap fit is experiencing at the top. Using this force, it's a simple matter to calculate bending stress at the base of the snap fit, which should be the maximum stress that the snap fit is experiencing. From there, we were able to use that to make an informed choice about the geometry of the snap fit and design it so that the maximum bending stress was 13.3 megapascals, which gives us a factor of safety of 2 using the ABS plastic.
A concern that the reflector mount brought up is the bending moment that it would create on the central pillar. The worst case scenario for the reflector mount force on the pillar would occur when the reflectors are in the vertical position. The force on the reflectors was analyzed using the highest non-thunderstorm wind in Las Vegas, acting normal to the plane of the mount at 82 miles per hour. A non-thunderstorm wind speed was used because it would be assumed that under known poor weather conditions, the reflectors would be angled parallel to the wind to mitigate bending stress, since no sunlight is available to reflect. The force created by this wind was found using a density of air of 1.23 kilograms per meters cubed, the area of one reflector mount at 0.63 meters squared, and the wind velocity of 82 miles per hour. The area was multiplied by 2 to accommodate for both reflector mounts, resulting in a force of 1,037.4 newtons on the central pillar. Next, the bending stress was calculated using this force, its vertical distance to the supporting point of 0.62 meters, the distance from the neutral axis to the point of contact of 42.5 millimeters, and a moment of inertia found using the inner and outer radii. The stress was calculated to be 4.56 megapascals, which is much less than the yield strength of the PVC of the central pillar of 24 megapascals. The results of this analysis would confirm that with the reflectors in the worst case scenario vertical position, with a normal wind force at the highest recorded velocity, the central pillar would not fail due to bending.
Now let's talk actuation. Our actuation subsystem is comprised of two PVC pipes, which also serve as our two axes of rotation. So the first is going to be this central PVC pipe that serves as our azimuthal axis and is driven by an azimuth motor. It has 350 degrees of rotation due to this mechanical stopover here, which is to make sure that none of these wires get bent or tangled up or otherwise unhinged while this axis is rotating with the altitude motor. The altitude motor is a stepper motor, and it is driven with a cog and a belt and also teeth on this crossbar. And this actually rotates the full 360 degrees as a safety configuration or for safety concerns. The azimuth axis also has a limit switch down here to, again, help us better control the DC gear motor. And also we have the altitude motor placed in the central pillar to protect it from the elements and sun and wind and any other not ideal conditions for inclement weather. So keeping in mind the design intent, ultimately this design is to be a cost-effective prototype. So we chose PVC for the structure because it's really good for prototyping applications. It's easily assembled, it's easily sourced, it's easily modified, and you could modify it with a standard bandsaw or a standard drill, and it's also cost-effective. This design actually uses 15 unique parts, including fasteners, so it's, again, modular and easy to put together, so it serves well for a prototype. Structurally, we're concerned with bending factor of safety. This is going to be the primary mode of failure. Assuming a worst case scenario of 225 newtons at a distance lever arm of 0.3 meters away from the central pillar, we can calculate the bending stress for this critical point right here. I don't know if you can see my pointer actually. Can you see my clicker? Okay. We can calculate the bending stress for this critical point and where the crossbar meets the pillar, and that is 3.25 megapascals, which, basing it against a 24 megapascal yield strength of PVC, we can calculate the factor of safety is 7.4. And we can confirm that this is the primary mode of failure because the shear factor of safety is much, much higher. Under the same loading conditions, we get that the maximum shearing stress is 0.38 megapascals, which gives a factor of safety of 63, which is, again, much higher than factor of 2. But because we're using PVC and also a belt, we need to be concerned with linear thermal expansion in PVC. We're concerned with the expansion along the length of the belt, which is 2.12 feet. So if you can see this graph extrapolating from this at 135 degrees Fahrenheit of maximum surface temperature, which is what this design should be rated for according to customer needs, PVC expands 0.0495 inches per foot, which gives a maximum deflection of 2.7 millimeters. Using the mechanical properties of neoprene, we can see that the functional stretch of neoprene is on orders of magnitude greater than 2.7 millimeters, so we know the belt will not snap. But on the opposite end of the coin, what if the belt could go slack? In neoprene, we see 0.00024 inches per foot extension for every 10 degree Fahrenheit increase. So at maximum surface temperature, the neoprene is going to expand at 0.0324 inches per foot, which is less than the rate of expansion for PVC. So we know that the belt is going to stay in tension. We also know that because the belt is not extending very far, we're not going to see significant tooth geometry deformation, so the belt will still be operational. Azimuth motion is driven directly by this DC gear motor with 22 Newton meter holding torque and 57 RPM maximum speed. The manufacturer suggests using this in things like lifting garage doors, so just intuitively guessing it should be sufficient. But to confirm, at very slow speeds, we can assume that it's delivering very close to the 22 Newton meter holding torque. So turning the structure about the radius of the central pillar, we get that it can turn 314 Newtons, which is more than the weight of the structure that it needs to turn. But beneficially, if we test this environmentally and we find that extreme wind forces or something crazy prevents the motor from operating, there's plenty of space within the base structure, and the base plate right here is easily modified by this dimension, this diameter, such that the motor could be further sized up to spec for different torque requirements. Altitudinal actuation is going to be guided by this servo stepper hybrid motor with 4.5 Newton meters holding torque and a 57 RPM max speed. Because we're meshing this with a cog and a belt and the crossbar, we have more of a deep dive into the power. So we know that we want to turn this weight at 0.1 degrees per second. So that's going to be 0.00175 radians. So working back from reflector to crossbar, those are going to be spinning at the same speed. We'll see a speed up from crossbar to cog because the cog is smaller in diameter than the crossbar, resulting in the fact that the motor is going to need to turn at 0.0034 radians per second. Speccing this with the inversely proportional relationship between torque and speed for a motor, we can find that based on the holding torque, actually we're going to be delivering 4.497 Newton meters of torque for this application, which is very close to the holding torque because again, we're moving at very slow speeds, which is about 15 milliwatts of power, assuming 65% efficiency for the motor and cog, 94% efficiency for the belt, and no real efficiency losses between the crossbar and the reflector mount because they're mechanically locked with those fasteners and bolt configuration. We are getting that we're delivering 0.0093 watts of mechanical power, which is going to deliver 5.31 Newton meters of torque, but we're turning this about the crossbar. So we know that we're delivering 133 Newtons of force, which is again, greater than the 125 Newton goal that we needed to deliver for this motor.
All right, I want to go into the controls aspect of this model. We wanted to use a microcontroller board. This is modeled here as an Arduino, but other similar boards such as a Arduino or the Wi-Fi enabled ESP8266 would also work for the configuration that we have here. We also have two motor drivers that will interface with the actuation subsystem to have both the DC and stepper motor be driven and connected in just via wall power to the 12-volt adapters. If I could have the next slide. So keeping in mind that our final design was focused on taking these customer needs and keeping our hedgehog concept in mind of simplicity and want to keep it cost effective, that taking into account my motivations and goals for wanting to have the lowest amount of parts using mostly off the shelf, while also taking into account keeping the tracking error and loop time low, while also having the light accuracy be as accurate as possible. I can take the next slide. So my goal for the control technique that we were actually going to use was keeping the sun tracking error below 0.5 degrees in order to allow the reflected angle error to be below 10%. And so in order to achieve that, we decided to go with an open loop algorithm-based control scheme where it would take the location data for the specific spot of each individual heliostat model, and then using an algorithm such as the Minkowski or the Blanco-Murillo, which have a 0.01 degree error rate, way below the 0.5 degrees errors, using correction factors such as atmospheric refraction, solar elevation, such as other factors in order to calculate the sun position and allow the individual heliostat model to take that information and interface it with the central tower in order to provide accurate tracking. I can have the next slide. The main concern with this model was making sure that the controller wouldn't overheat, that the temperature that it was going to get to was going to be within its operational range of about 25 degrees Celsius to 85 degrees Celsius for the varying different parts that we have inside of here. And so to take this into account, we just made a simple thermal circuit, taking into account an ambient temperature of 47 degrees, which is already the hottest temperature that we would have seen in the area that we were designing for. And after running these calculations, taking into account the different thermal conductivities of the different pieces we have, This is another reason that the CPVC was so useful, because of its low thermal conductivity. It actually shielded a lot of the heat away from the Arduino model that we have here. And after taking all this into account, we got a final temperature. The Arduino would only be experiencing 55 degrees Celsius, which is way below its 85 degrees Celsius maximum temperature that it can operate at.
And now we will talk about the base subsystem. The base subsystem is made out of square PVC tubing, and the roots for the base subsystem are made out of regular PVC pipe. The base subsystem has a door and also a mount for the actuation interface so that it can hold the motors and the control components for those motors in the base. And the door can also be open and closed for easy access in case repairs or maintenance are required. The base is meant to be buried under 0.5 meters of sand so that it does not tip or move under high winds. Next slide.
All right, so we were able to meet, oh, you want to go back one more? Perfect. So we were able to meet 6 of the customer need statements with having a low cost, simple design, like our hedgehog concept. So with using less than 5 parts, we were able to keep our design very simple and low cost with a high structural integrity.
And this right here is a diagram of the soil force calculations, along with showing the wind force that would be affecting the central column. The calculations show that the PVC roots would be able to withstand the pressure of the sand at a depth of 0.5 meters. Further testing and simulations would need to be done in order to see as to whether or not the base would tip if this wind were to press on it, since the sand itself requires a very complicated kind of calculation to find an answer to that question, because the sand is made up of many tiny particles. So further testing and prototyping would be necessary for this step.
Our last topic is perhaps one of the most important, the cost analysis of our heliostat module. So the production cost, as you can see, would come out to around $124 per module. This is the per module cost. While the cost of creating the prototype would be around 2.5 times that at $326. The bulk of the cost for both the prototype and the production module comes from OTS parts. Mainly that's because of motors and a couple other things that go with the motors, such as the cog that drives the pulley and the timing belt that we use for the pulley as well. Modified OTS parts actually tend to be very cheap because that was just our PVC piping. And then the raw materials is solely comprised of the ABS plastic used to mold the reflector mount. As you can see, many of the costs drop significantly when we move to production because of bulk discounts. Purchasing raw materials is a lot more efficient. Purchasing PVC piping is a lot more efficient. And we can also get discounts on many of the OTS parts. However, manufacturing labor and assembly labor stayed the same per module for obvious reasons, as well as energy consumption. Unfortunately, each heliostat module is actually slightly larger than 1 meter squared. So the cost that you see here is not the per meter cost. The per meter cost would actually come out to around $117, so a little bit lower. However, this still misses our target of $100 per meter squared. So more methods of saving cost should be explored should you go with this design. Maybe such as leveraging connections in the industry, or something better to investigate might be manufacturing the OTS parts that are expensive yourself instead of buying them. So if you could make cog gears for cheaper than the OTS part costs, or even making the motors in-house or having them custom designed to be as cheap as possible. Unfortunately, we weren't able to investigate that ourselves in the short design time that we had. So that's just all we can suggest to get the cost down.
The intent of this project was to design a small-scale heliostat for industrial solar processing that exceeds the customer's expectations. Our design is a relatively low-cost, simple heliostat that is highly efficient and highly functional. We purposefully designed our heliostat with fewer parts that can be easily assembled and readily sourced to make solar thermal power generation more accessible and scalable. And that concludes our presentation. Thank you all so much for taking the time to visit us. Our contact information is listed here if ever needed. We will now open up for any questions.
Hey guys, this is Tom Singer from Northrop Grumman. The first question I got to ask is, that is an enormous reduction from a prototype cost to a production cost. And I'm not sure that I buy, especially when you're talking about buying off the shelf parts. I'm not sure that I believe that you can cut that by a factor of like 2.5, I think it was. Like how reasonable is that? Where, I mean, you're buying 1,000 or 2,000 motors, right? You're not, you know, building a plant to build motors here. So I don't know that I could see that coming down quite so much.
Sorry, just unmuting myself. So I think the cost of the OTS parts came down by about a half. A lot of them were sourcing from like Alibaba.com and stuff like that. And so they did have different prices for the sizing of the order. They're not the highest quality motors, but we do think that you would actually see a reduction in price that is about that much. We should ideally contact those manufacturers to make sure, but we didn't have time, unfortunately.
Okay, yeah, that's something that I'm not sure I'd buy, but okay. Let's see. From a structural efficiency standpoint, because I'm a structures guy, so I like to pick these sorts of things. You've got an analysis of your vertical member subjected to what, 90-mile-an-hour winds or something like that. And he said we're good for 90-mile-an-hour winds, and if it's higher than that, we'll go into a safe mode, and that's okay. Then you did your analysis of your crossbar for the weight of your heliostats. But as far as I can tell, the crossbar is going to be subjected to load from 90-mile-an-hour winds as well. So why is that not a load case on your crossbar?
That's a really good point. Frankly, most of my analysis was just about like trying to make sure that weight-wise it could withstand it. I have to imagine that if we were subjected to like 1,000 newtons of force rather than like the 200-ish that I was estimating with, that's going to make our bending stress more like, what, 3 times 5 is 15. So that's still technically under the yield strength of PVC. So I think we should be fine.
Okay. Yeah, you should probably be fine, but that's certainly a load case you should consider. It's interesting to me because a lot of teams have looked at, oh, we've got like a 90-mile-an-hour load, and the pin that connects our mirror to our system is going to survive, and that was as far back as they chased it. And you got to chase it back to ground, but you guys chased it back to ground or almost to ground, but like forgot everything in the middle. So don't forget that. But speaking of chasing it back to ground, how is this thing held to the base? I think you did the analysis at the base of the vertical pole, and I didn't see any analysis of the connection at that base.
So if I remember correctly, the connection to the center column to the base is this weird fitting that I believe one of the members found it on like Alibaba or something. It was a weird sort of fluted, well, I don't know if it's fluted, fitting that just like you screw in. Well, I think we just screwed in. I didn't do any particular analysis on that portion because I did a little bit of analysis to see if like the center column would break from like the wind. It was fine. But I never actually did any analysis on whether or not the connection itself would break.
Yeah,
Because
connections
after that,
tend to
I
be
was-
weak points, so I'd recommend
Yeah.
doing that.
Yeah, it would concentrate
will
the
say-
stress most likely.
We're using like M16 steel fasteners, so they're pretty beefy. So we're drilling it into like a 20 millimeter thick PVC pipe. So I'm kind of hoping that they will still do their job that they're supposed to do.
Are you threading PVC to hold those? No, yeah, those are connected with nuts, right?
Yes.
Yeah, I guess where I would expect a failure to happen is in like the flat plate of the top of that base. That's kind of where I suspect would be problematic. Let's see other stuff. I wrote down a lot of notes. You had well, actually, while we're looking at this, could you actually flip back to the slide we were just on? What drives the orientation of those sort of diagonal supports in your mirror? Like what's loading those and why are they oriented in the way that they are?
We didn't do detailed calculations or FEA to figure out the geometry of it. We just figured that we wanted to keep, obviously, the outside of it, don't remove material there. And then so the triangular cutouts are not optimized is what I'm saying. It was more just looking at it and deciding like, oh, we know that the maximum bending stress is going to be right next to where it's mounted. So
But the intent here is like an injection molded part.
Yes. Yeah.
Okay, so I would suggest that, I mean, the primary loading on those is going to be axial to kind of keep the overall rectangular shape of your structure, but then bending as well as it's supporting wind loading on the mirror. And that's not a very good shape to resist bending if it's like wide and flat as opposed to like thin and tall. Would be a more structurally efficient shape. And then I gotta ask, why does that center post extend significantly above your crossbar? What's up there?
Mostly that's because standard sizing, and as we kept downsizing and moving things around, this was how the standard sizing was when we bought it.
Okay, I would suggest if you're purchasing parts in bulk, cut that down. And then you said that this is designed out of PVC because it's easy to prototype. Are you designing a prototype or are you designing a product?
We're designing a product, but the design intent for this particular design is ultimately like all the teams are prototyping something together. So it was with the design intent of like, this is something that's like conceptual that will be scaled up. This is a good way to start. This is a good starting point because it'll still be cheap as we scale up because it's again, PVC.
So what do you envision your product looking like? Is it still going to be PVC?
I would think so, yes, or something cost-wise similar, just because it's, again, so easy to put together.
Okay. All right, I'll see if anybody else has any questions.
Any other questions from our panel?
I've got more. So you have a belt drive that's running down the axis of this center post, right? Is there any ability to tension that belt, or is it just kind of it is where it is, and wherever the motor lines up relative to the crossbar, that's how much tension it's going to have?
I mean, it's designed to be like, it's designed dimensionally to be a little bit tighter to kind of offer already being in tension, because we're just going to buy it like already sized standard, which is part of the reason why the crossbar is located where it is. You could technically put a tensioner on it, but again, going back, we're just moving so slow that I think the tension that's already in the belt should be fine to support. It's not like we're spinning it at like 60 RPM and like creating this like death machine heliostat. So it should be fine for the power transmission and things like that.
I mean, you say it's not a death machine, but you haven't been near the collector yet.
maybe just
Speaking of the belt, you mentioned that you're going to have some sort of like cog on the crossbar itself, internal here. How does that cog get attached to the crossbar?
It's technically not a cog, so you can buy. We're buying one size of timing belt that's for the actual like belt that's driving it, and then you're buying another that's the diameter of the crossbar that you can like kind of like squish and slide on and locate it that way, and then possibly attaching it with adhesive if it needs to be more stable.
Okay, so that's going to be like a slip fit over the crossbar, which will be a challenge, but probably not a nightmare to assemble. Although once you glue it in place, it'll be a nightmare to disassemble if you ever needed to do that. But I think that's pretty reasonable. Let's see. You'd mentioned you did a thermal analysis of the bar, and you said, oh, it'll get up to 47 degrees Celsius or so in Las Vegas, and not being a metric guy, I don't know if that's hot or not. It sounds pretty hot. And you said, as long as the temperature is within that, the belt will be fine. And then you said, I think you did like a comparison of CTE, and you said the belt will always be in tension. But I'm pretty sure it gets cold in Las Vegas too, right?
This is true.
Okay, so that might take the bolt out of tension, especially if you don't have a tensioning system. So maybe consider that. I don't think it would be a problem as long as you start with some reasonable amount of tension, but worth looking at. What about wear? You've got things rotating, sliding past each other. What are your wear concerns here?
I figure the primary wear concerns would definitely be between the crossbar and the pillar, as well as the pillar and the weird bass trumpet joint that we found.
Mm-hmm.
Honestly, we don't have detailed calculations on wear, but considering that it's just PVC on PVC, I can't imagine it would be too bad, so long as they weren't completely roughly cut. But that could also be something that you could definitely put something within the like the hole for the central pillar, or add some kind of like lubricant to the base joint, or like some kind of oil just to kind of help that along.
Yeah, I suspect you might want to have some sort of bushing surface on there. I guess the other thing I'll note is if all you've got is just a belt drive and it's sitting on a cog, there doesn't seem to be any like lateral restraint of that crossbar, right? So if I come and I know you can't see my finger, but if I push on the edge of that crossbar, is there anything that's going to hold it in place in the vertical bar?
Hold on, I'm trying to look for a picture as we speak. This guy up here is a 3D printed like washer that kind of fits on, and there's clevis pins and cotter pins on either side that they're like drilled into the crossbar, so it keeps it mushed to the central pillar properly. Okay,
gotcha. Let's see. I'll say I appreciate you were thinking about the field, right? A lot of teams are coming and saying, hey, here's our single module, without a lot of appreciation for the fact that this is going to be in a field and they're going to be varied distances away from a collector. So I appreciate you were thinking about that. When you're talking about the angles that you're reflecting the sun at, I certainly appreciate that. I'll mention to you, I haven't mentioned to anybody else. When we're talking about insulation, right, we're talking about 1,000 watts per meter squared. That's kind of like baseline high noon insulation on Earth's surface. How much of that comes directly from the sun, and how much of that comes from like the scattered rays of the sun?
Wait, I'm not sure I understand the question.
Right. So when you look up at the sky, right, the sky's blue, not black, right? So yeah, sunlight is being scattered by the atmosphere, and it's not all coming down to you or to your reflector on a straight line, right?
Oh,
most of it's coming down on a straight line, but based on my quick Google search a couple of days ago, about a third of it is actually being scattered, and so about 300 or so watts per meter squared is coming in at some non-direct from the sun angle. And if it's coming in at a non-direct from the sun angle, then when you reflect it off of your mirror, it's not going to go in the same direction that the sun, like the direct from the sun line, is going, right? So you're starting off probably only able to reflect about 600, 700 watts in the direction that you intend to reflect it.
Oh, I see what you mean. Yeah. Yeah.
So
So
I think that's
um,
going to go into your field size.
yeah, definitely. That's why when we calculated the 960, we definitely didn't take that into account. Again, like ideal conditions, not even realistic, I
Mhm.
suppose.
All right, so let's talk more about that, right? So the customer said this is a 1 megawatt plant, right?
Mhm.
And so you say, okay, so we've got whatever we're reflecting back, we need so many of these. How long would they like to be able to generate 1 megawatt in the course of a given day?
Yeah, that's the other thing, because I did some calculations for like heliostat angles and stuff,
Mhm.
but that was all based on weather conditions, like solar conditions on the winter solstice at
Mhm.
noon. So the winter solstice is typically the worst day for solar power, just
Mhm.
because the sun is so low in the sky. So we know that in terms of positioning, the heliostats can still get the maximum amount of light into the receiver, but we didn't consider like the length of day or anything like that.
Yeah, I think
Yeah.
that's maybe something where the customer may have written a poor requirement. Yeah, Carol's asking to ask questions, so I will certainly yield the floor.
Okay, on the deck of slides that you turned in, I think it was page 28. So who did the picture, the diagram, the wiring diagram?
Devin?
So that would be me.
Okay, so what did you use to do the wiring diagram?
I actually just spliced together a couple of pictures and then just like,
Oh, okay. Because to me, it looks like there's this great freeware program called Fritzing that, will do that stuff for you, except that you need to recognize when that's used. So in your wiring diagram, I don't see any limit switches or encoder or any. So the stepper motor, when you step it, for low speed, you should be able to assume you're not going to lose any steps. But other than that, do you have any way to sense where you're at?
so yes, we did actually have a limit switch for the DC motor.
We also have one in for the.
That's
stepper motor
right.
as well.
Okay. I saw them in the CAD drawings, and it's good that they're in there. And if you spec out how much they cost and all of that, that's the majority of the design. Don't forget to hook them up.
Yeah.
So did you have an encoder for the DC motor or a potentiometer or something?
We did not.
Okay, so whatever design you prototype next, you will also need something to sense where you're at. And that's it for me. Thanks for taking my question.
Thank you so much.
Okay. So, oh, sorry, I was going to wrap things up. Tom and I are having it.
Oh yeah.
Yeah. So, well,
I got more to say on that too. I've written it up in the notes, but I haven't really like unloaded it on anybody yet.
okay. Well, I mean, we do. I don't know that this group is so good. I don't know that we want to unload on them.
No, you did. I certainly don't mean that as like you did a bad job. I think you did a very good job, and all the teams really have done pretty good jobs here.
Yeah, I also, I guess just for, full transparency and disclosure, struggled a lot with the 1 megawatt requirement and the 1,000 watts per meter squared, and went back and forth kind of behind the scenes with the customer a lot. And they held firm that that's what they want. So
Who is the customer for this?
the customer is John Sheffy and Jim Trainum and Hitomi Greenslit, who run the Renewable Energy Conversion Laboratory at UF.
Okay.
Yeah. So at the end of the day, I came to the conclusion that they probably know more than I do about solar energy. And so I'm going to stick with their requirement, even though honestly, it did not make sense to me either.
Maybe. Yeah. The 1,000 watts per meter squared, right? That's like on a flat surface, like normal to the sun, right? So if you're pointing your mirror and the sun is directly normal to that surface, if you're at ground level, that's 1,000 watts per meter squared. But unless your tower is like almost directly in line with your mirror and the sun, you're not going to be directly normal to the sun to reflect 1,000 watts per meter squared, right? You're going to be at some like tilted angle. And so if the sun's like directly up here and your tower is over here, your angle is going to be like that. If I can hold my hand, right? So you no longer have 1,000 watts per meter squared when the sun's coming straight down, right? So, and every mirror in your field is going to have a different angle between the sun and the reflector, or the collector rather. And so you're never going to hit a situation where every mirror in your field is collecting that 1,000 watts per meter squared.
Okay,
So
because
I
they'd all
think
have to be
there's certainly
completely
some, like,
flat. Okay.
Yeah, there are like field things that come into play here beyond just a single module, which again is why I appreciate that you started thinking about like, what does this mean for our field, right? So I definitely like, I think like follow that line of thinking.
Yeah. So the customers did actually provide the class with like a calculation technique that includes, Tom, what you're describing. There's a cosine theta effect.
Yeah.
That cosine theta relative to where the I'll call it a pointing vector, where the solar reflector pointing vector is pointing versus where the sun is.
Yeah.
Like the cosine of that angle, of course, reduces the total energy. And so at least in theory, and I think at this point, every group has done this, all of the groups should have gone through and done the 1 megawatt calculation using the model provided by the customer. So, and like I said in chat, again, it's a weird requirement, but the customer, so maybe we go back one step. In the summer, the customer wanted 1 megawatt basically 24 hours a day. I mean, it was weird. They're like this, we should be generating 1 megawatt of power whenever the sun is up. But you know, the sun in the early morning is on the horizon, and in the evening, the same story. Yeah. And there's just no way to generate a megawatt of power. And so then we were sort of having to fudge, you know, what do they mean by 1 megawatt all the time? And different groups, as you remember, had like much different sizes of their solar fields and much different costs, because that customer need was interpreted differently by every group. And so we ended up changing the customer need so that it's a megawatt one time per day, but 365 days a year when there's no clouds.
Yeah. If I were the customer, and granted I'm not, and these guys are certainly smarter than I am about things, but if I were the customer and I was designing a power plant, I'd want to know, you know, this is the amount of power I would like to be able to deliver over a period of, you know, 6 hours during the day, right? And you know, maybe you design to achieve that, and you figure out like, you know, 6 hours a day for the course of the year, this is how much power I can deliver. The peak power, I don't think I'd really be that interested in, because if I exceed the peak, like I don't want to like melt things in my collector, but if I exceed the peak, I can just like move a mirror and not collect that. So it is a weird requirement. So it's definitely something, and I'll say, like, as an engineer, you'll learn that customers are often not great at figuring out what they want and writing requirements for it. So sometimes they need to be coached.
Yeah, true in the academic world as it is in the real world, for sure. Okay, awesome. Well, so we're way over time now. The good news, I guess, the silver lining is that we have
a break.
Yeah, we have a break built in so that we could spend a little bit of extra time with this group and with this discussion, which I'm happy that we had. But just so that everybody does have that 5-minute break to, run and refresh and grab coffee and stuff. So that the last two groups have a fresh panel. We'll wrap it up there. I want to just this was group 8, right? Yeah, I want to thank group 8 for sharing your design with us. You guys know this one was one of my favorites. So I appreciate all the hard work you guys put in this semester. And I'm really hoping, I don't know how many of you guys are coming to Mech 3, but I'm hoping that this is one of the ones that gets prototyped. So when you get into your groups, fight really hard for this one, because I think it's a good one. So thank you.
Thank you. We're
Thank
also
you so much.
manufactured.
Very good. Okay, we'll stop recording.